Neutrinos are subatomic particles. They are electrically neutral, which means that they do not interact with electromagnetic forces. Since they do not interact with electromagnetism, that means with light, they can't be seen at all. Neutrinos only react with gravity and nuclear decay.
Since neutrinos are electrically neutral, they're not affected by any electromagnetic forces. They're only affected by weak subatomic forces with a much shorter range than electromagnetism. This enables them to pass through great distances in matter.
So there are 3 types of neutrinos known today. Each type, or flavor, of neutrinos are related to a charged particle, which gives it its name. Hence, the electron neutrino, which is related to the electron. And the other 2 types of neutrinos, the muon neutrino and the tau neutrino, are related to heavier types of electrons.
No definite mass has been set for the neutrino. There are many comments on how it doesn't have a mass at all. But this raises many theoretical problems to set the range of a neutrino.
So here's the problem with neutrinos not having a mass. Neutrinos oscillate, or change from flavor to flavor. So if they didn't have a mass, they wouldn't be able to change at all. In fact, they'd be stuck as one certain type. But since they do change, it's obvious that neutrinos have some finite mass.
Neutrinos are passing through your body at vast numbers at all times. It's flooding out of the sun through its central furnace. Even when it's nighttime where you are, those neutrinos are passing through the Earth and your body as though the Earth wasn't even there.
Another thing that occurs is cosmic rays. Cosmic rays are high-energy particles flying in from deep space, and they often strike with atoms in the high atmosphere. This will produce a vast number of neutrinos that will also go right through you.
A neutrino can only be detected when it interacts with matter we can observe. Since it interacts so little, a neutrino would have to pass through a block of lead, a light year long, before it hits an atom and is detected.
So what about the history of the neutrino? Well, the idea of the neutrino came up in 1930 by a man named Wolfgang Pauli, who suggested the idea. This came from the issue of radioactive decay and how a certain amount of energy should have been emitted, but not enough was detected. So this energy was pretty much disappearing and no one knew what it was. So Wolfgang Pauli came up with the idea that energy was being emitted through these particles that could not be detected because they had such little mass.
So what do these particles have to do with astronomy? Well, to understand the universe, we must understand the characteristics of a neutrino. As the theory goes, neutrinos were created in the Big Bang and diluted after the universe expanded. These neutrinos are emitted from the sun and contribute to the universe's energy.
Neutrinos are unique, got no mass, no charge. There's no way of seeing them, they ain't that large.
They come in 3 flavors like a pack of ice cream, electron, muon, tau, which are never seen.
Neutrinos are created from nuclear decay. There are trillions of them in our Earth every day.
If you want an example, okay, here's one, the nuclear reactions that take place in the sun.
From Geneva to Italy, you gotta be kidding me, violating symmetry of special relativity.
Muon neutrinos moving faster than light, superlumino, time of flight.
These subatomic particles shoot from the sun to the Earth, trillions in you, since your mother gave birth.
Nothing can stop these neutrinos from passing, penetrate material without interacting.
Einstein said there's nothing faster than light. Wolfgang said, oh man, you ain't right.
These particles are invisible, they're also indivisible. You better listen up, cause this info is applicable.